Hello, good day. My name is Oluwaseun Oladimeji, and I'm presenting the value of operational coordination for EV fleet aggregators. The transportation sector has been known to contribute about 25% of global CO2 emissions. And because of this, climate mitigation efforts have been geared toward electrifying the transport sector. Coupled with this, car makers are also evolving to become mobility companies. And energy requirement for these vehicles becomes a pressing question for the distribution network operator. The popular solution to this has been the use of valley filling, which tries to keep the peak of these EV loads to periods of lower consumption, of general lower consumption. But there is a probability that this peak is also, that another peak might be formed during this time. And thus, we are presenting a way of co-optimizing the EV fleet and the distribution grid. That is to say, we are trying to include the EV aggregators to be also part of the distribution network operator management. The model of incomplete information, basically, which serves as a benchmark for our problem, is what we present here. This is the Alman model of incomplete information. And the assumptions here are that for each EV aggregator, they have specific knowledge of some parameters of other EV aggregators. And we're also going to be looking at the aggregator aware users, which is what you do when you order an Uber, and the aggregator blind users, which is what you do when you take the public transport. And for our cooperative model, we are going to use the core, which basically which basically says that when you are involved in a coalition, you want to be better off than when you are acting alone. That is, when you are receiving benefit in a coalition, should be much better than the benefit you get when you are acting alone. And the Shapley value will be used for cost computation for each lead owner. What are we trying to optimize? We are minimizing the cost of travel and the cost of energy, and we are subjecting them to the routing constraints, the distribution grid constraints, the energy balance, and of course the stochasticity that the demand is based on. We got real data from New York City, from downtown Manhattan, which included the pickup and drop-off location and time, the passenger count, the waiting time, and the power consumption at each charging station. The blue triangles in this picture, they are the charging stations in downtown Manhattan. Quickly to the result. We have the aggregator aware and aggregator blind result. For the aggregator aware, basically like you taking a Uber, the aggregator 2 might just be a Uber, which is the most popular, or it has the highest number of assets that people are very familiar with. So yes, it has the highest value function, uses the highest amount of energy. But when it comes to the aggregator blind result, we're talking about proximity to the demand. And aggregator 1 actually takes the cake here. And when we now bring, and I should mention that these two, the top results are the ones when the aggregators are acting differently. But when we get involved in a coalition, we see that there is a reversal of this. So I would like you to focus on the green triangle. Let me show it on the next slide. So it's showing that the aggregator 1 has a negative cost because, of course, like I said, it has the best proximity to the people that are demanding the transportation service, and followed by aggregator 3, then followed by the aggregator 2. So the aggregator 2 contrast to the aggregator aware users actually has the worst cost in our case. The core is basically shown here in the dark gray triangle, and the Shapley value is shown by the red. And here we see that yes, there is a true solution to this problem. We tried to analyze other problems involving 4 aggregators, and there was even one we analyzed that involved 5 and 6 aggregators. And we're able to delineate, that is, we're able to analyze each of these solutions because it was still computationally okay. I mean, with 6 aggregators, you have almost like 63 coalitions that you can analyze, and we could do that quite easily. And we see that there is a general trend of decrease in cost and energy as the aggregators actually increase, because you see like there is this efficient distribution of passenger demand between the aggregators as their numbers increases. And the relative location of fleet also matters a lot, just as we see in what I described in the previous slide. And based on the market structure Negative cost is possible, and would aggregators can receive extra payments based on this. These are the references and acknowledgements, and I really thank you for your time and attention. If there are any questions, I will be ready to take them. Thank you.